Right, hi. In this video we're going to look at Lewis structures. We're going to look at how to take a molecular formula and draw a Lewis structure from it. In this technique we're going to do the 5 following things. We're going to count the total valence electrons, we're going to arrange the atoms, we're going to give each atom on the outside 8 electrons, we're going to then fill up the central atom and then confirm whether we have a correct Lewis diagram or we need to move some electrons to make double or triple bonds. We need to remember when we do this and we do Lewis structures that every atom wants to gain an octet, apart from hydrogen that's looking to have 2 electrons in its outside shell, and there's a couple of exceptions here, beryllium and boron, that we'll look in as we go. So let's have a look at our first example here, HOCL. So we want to draw the Lewis structure for this. Basically what we want to do when we draw the Lewis structure is the first thing we do is we count the total number of electrons. Now when we count the total number of electrons, what we do is we look at the periodic table, and let's say we had hydrogen on the periodic table and we see it's in group 1. So therefore hydrogen has 1 valence electron. We go along and we find oxygen is actually in group 16. That means it has 6 valence electrons. Chlorine, being in group 17, has 7 valence electrons. So we add these up, 1 plus 6 plus 7, we get 14 valence electrons in total. The next thing we want to do is arrange the atoms, but in order to arrange the atoms I have to work out which atom has the most unbonded pairs of electrons, or unbonded electrons. So let's have a look at this. Hydrogen has 1 valence electron, so I'm going to draw a Lewis dot diagram for it. There it is. So it's got 1 unbonded pair, or 1 lone electron there. Oxygen has 1, 2, 3, 4, 5, 6. So notice I've drawn 1 in each of the 4 points of the compass, but I've paired up 2. I end up with 2 non-bonded electrons. So here I have 1 bonded, not non-bonded, non-paired. So 2 non-paired electrons, 1 non-paired electrons. And I go to chlorine and I go 1, 2, 3, 4, 5, 6, 7 valence electrons. I've got 1 unpaired electron. So chlorine has 1 unpaired electron, oxygen has 2 unpaired electrons, and hydrogen has 1 as well. 1, 2, 1. The one that I put in the center is the one that has the most unpaired electrons, and that's oxygen. So oxygen's going in the center here. I'm going to put hydrogen on one side and chlorine on the other. Okay, so I've got 14 electrons. The next thing I want to do is give the full allotment to each outside atom. Now here I've said give 8 electrons to each outside atom. That's 8 electrons to each outside atom except hydrogen, that gets 2. I put the first couple of electrons in between the hydrogen and the atom adjacent to it. And now I'm going to put 8 around chlorine, 2 here between the oxygen and the chlorine, 2 on the top, 2 on the side, 2 on the bottom. And now I've allocated all the electrons to all the outside atoms to have their full allotment of electrons. Notice that I've used 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So I have, let's see, let's do this again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. I've got 4 left, so they go around the central atom, the extra 4 electrons, 2 on the top, 2 on the bottom. And now I have allocated all of my electrons. Now I just want to check that now I've allocated all my electrons, that all of my atoms have their allotment of electrons around them. So let's check that each atom has 8, or hydrogen has 2. So if I circle here around the hydrogen, and this is just an imaginary circle, I wouldn't do this on the paper, I see that hydrogen has 2 electrons adjacent to it. So it's satisfied, it has 2 to fill its shell, its electron shell. Chlorine has 8. So it will also fill its electron shell, and oxygen has 8 around it, so it's satisfied as well. So all of these atoms have the required amount of electrons around them. We have used exactly the 14 electrons we're given, so we are happy now that this Lewis structure is correct. What I might want to do is any electrons that are between atoms are bonding electrons, and I can replace 2 electrons with a line to represent the bond. Notice I can't have the electrons and the line at the same time, but I can put either the 2 electrons or the line in my Lewis structure. So this is my final Lewis structure here, and it's often how it is represented. So let's look at another example. This is carbon disulfide, and first thing we want to do, remember, is to count the valence electrons. We might notice that carbon is in group 14, so it has 4 valence electrons. Sulfur is in group 16, it has 6 valence electrons. So I have 4 plus 2 6s from each of the sulfur. We have 16 electrons in total. I now need to arrange these atoms, and again, if we look at the carbon atom, we notice that it has 1, 2, sorry, let me just do that one again. Let's do the carbon. So it has 1, 2, 3, 4. It has 4 electrons in total, and each one of them is a single, so it's not a pair. So there are 4 electrons that aren't pairs. That means it's going to be the atom in the center, because, well, that's the maximum you can get. With the sulfur, we have 1, 2, 3, 4, 5, 6. There are 2 unpaired electrons. So the most unpaired electrons goes in the center, the carbon, then the sulfurs are placed around the outside. It has 16 electrons, so I'm going to put the allotment of 8 around each sulfur. 2, 2, 2, 2, 2. And then I'm going to put them around the next sulfur. And what you'll notice here is I have used all of my electrons, all 16. So let's check the atoms to see that they have the correct amount of electrons around them. So this here has 8 electrons, and we'll check the other sulfur, it's got 8 around it. But when we go and check the carbon, we notice that there's a wee problem here. We've only got 4 electrons around the carbon. This doesn't meet the requirements of a Lewis structure. A Lewis structure must have all the electrons accounted for, and each atom must have its octet around it, or 2 if you're hydrogen. So what we have to do here is we somehow have to give the carbon extra electrons without taking them away from the sulfur. So what we do is we take some pairs of electrons from each sulfur, and we're going to move them in between the sulfur and the carbon, so now they are adjacent to the carbon but still next to the sulfur. So we'll end up placing them like this. Notice I've just arranged the electrons on the outside of the sulfur so they're a bit more symmetrical. So this is forming what we call a double bond in between the sulfur and the carbon and the sulfur, and we can draw it, we can replace these 4 electrons in the middle with a double bond. So remember, we did this because we found the center atom did not have enough electrons. I had to shift one from a pair from the outside electrons. So sometimes we have to shift a pair. It could be 2 pairs. If there's 2 pairs, it's usually we shift one from one side, one from the other, and we make these things called double bonds. Okay, so the last example I've got here is one that often comes up because it's just a wee bit different, and that's boron. So boron trifluoride here is a bit different, and the reason it's different is because of our boron atom. Now our boron atom only has 3 electrons at the start. Right, so if you were to draw the Lewis structure for boron, you would have 1 electron, 2 electrons, 3 electrons. Now, if boron is going to go and form bonds with other atoms, at most it can only share 1, 2, 3 pairs. It can't share in this 4th spot because it has nothing in it. Now, what that means is boron, once it has its full allotment of electrons, only has 6 electrons around it. So boron, when we put it in a central atom position, is only going to have 6 electrons around it. So we're going to do this a wee bit different. We count the total number of electrons that are contributed here, 1 from the boron, 7 from each of the fluorines because they're in group 17, and we end up with 24 electrons. I then take these 24 electrons and we don't take the electrons yet. We arrange the boron in the middle and we're putting the fluorines around the outside. We're going to take now 24 of the electrons and we're going to give 8 to each of the outside atoms. There we go. Once we've done that, let's check to see that we've got the correct allotment for each of our atoms. So fluorine, check that one on the left here. Yep, it's got 8. The one on the right, 8. The one on the bottom, 8. And if we look at the green circle in the middle, boron has 6. Now it doesn't have 8, but boron doesn't need 8. Boron is an exception. Boron only needs 6. So now our molecule is satisfied. We don't have to move any extra electrons and make any double bonds. This is one of the exceptions. Remember boron. Remember the other one is hydrogen, but we're pretty confident with that because we see it in lots of examples. There is also a possibility that you might have to draw something that has beryllium. If you have beryllium, beryllium only had 2 electrons from a start, so it only has 4 in its outside valence shell. Okay, I hope this has helped and that you can get on and practice some more Lewis structures. Goodbye from Mr. T and good luck.